Hello everyone, welcome back to Academia Unplugged. If this is your first time seeing us, thank you so much for clicking on this video and for your interest. Don't forget to like, comment and subscribe, and also share so that other people can subscribe too. We are still on the road to 100 subscribers. And if this is not your first time seeing us, hi Unplugger, welcome back, and thank you so much for your interest once again. And for interacting with us and for interacting with last week's video. We appreciate you. So today on the platform we have Dr. Yin. Hello.
Hello.
It's very nice to have you today, and thank you so much for your time.
Thank you pleasure.
So much. Yes, thank you so much for agreeing to do this with us. We are very honored to have you on the platform, and we don't take your time for granted. So, would you like to say something? Sorry.
No, I thought you will introduce me first.
Yeah, for sure. I'm going to do that. I'll first introduce you, and then I will talk about your bio a little bit, and then after that you can correct me if I'm wrong about something, and then you can add on if you would like for us or our audience to know more about you. Is that okay?
Okay. That sounds good.
Okay, good. Are you ready?
Yeah.
Okay, so Dr. Yin, his name is Dr. Cangtao Yin.
Yeah, right.
Yes, Cangtao
right.
Yin. And Dr. Yin, so for, going forward, I'm just going to refer to you as Dr. Yin.
Yeah.
Okay.
Yeah, okay.
Thank you. So Dr. Yin is an expert in statistical mechanics, reaction rate theory, potential energy surface, and quasi-classical trajectories. And I think later on we'll get to know a little bit more about this and what that is. So Dr. Yin you did your PhD in Tianjin University in China.
Yeah, that's right.
This is from the year 2009 to 2014 at the Department of Physics.
Yes.
And then from 2015, you were at the Dalian Institute of Chemical Physics, still in China for a postdoc position. This was also, I don't know, was it sponsored by, or it's part of a state key lab for molecular reaction dynamics?
That's the lab's name.
That's the lab's name.
Yeah.
I see. Okay, thank you. Okay, and then from the year 2016 to 2019, you were at the Institute of Atomic and Molecular Sciences, Academia in Sinica in Taipei. This is in Taiwan.
Yeah, in Taiwan.
Yes, for another postdoc position. And then actually, before you finished your PhD, you were a visiting scholar in France at the Institut Harry Poincaré. I don't know if I'm saying that correctly.
I don't know that either. Yeah.
Okay, but this was for 3 months in 2013 from September to December.
Yes.
That must have been an experience for you.
Yeah, it's a beautiful city It's Paris, so.
Okay, I see. And then you were also, you did another postdoc at Szeged University. This is in Hungary.
Yeah.
With the, I don't know how to pronounce this, MTA-SZTE, so Institute for Computational Reaction Dynamics, or this is like a research group.
Yeah, this is also a group.
A research group, yes. Okay, that's great. And this is from 2022 to 2024.
Yeah.
I don't know if I missed something from 2019 to 2021.
That's COVID time. So, so I was at home. Yeah.
Okay. I forgot that there was actually once a COVID time.
Yeah.
That's bad. Yeah. And then so you are currently doing your postdoc at the University of Basel.
Yeah.
Okay, great. With the I think it's Dr. Marcus or Professor Marcus. group.
Professor Marcus
Muley group.
Yeah, Muley
yes.
group. Yeah.
Yes, I saw that. Congratulations on such an impressive academic journey. I think it's very impressive. When I was looking through your work, I was like, wow, we have a genius with us today.
Actually, no. I'm not.
Okay. And so you also, actually, this is very interesting. From what I found, Dr. Yin has first authored about over 15 publications. And from what I found, it was 24 publications, and he's been involved with about 32 publications altogether that are in relation with physical chemistry and chemical physics.
Yeah, that's actually similar. Similar field. Yeah.
That is mind-blowing. Yeah. As a PhD who's trying to publish their second article, I'm just like, how did you do that?
Because I spent like 10 years, so of course I get more.
Well, I still think it's very impressive. Congratulations on that.
Thank you.
It's a pleasure. And so would you like to add anything, or would you like to correct something from your bio?
No, you did nice work. That's all.
Thank you. Okay, so now we are going to get into the part where we have icebreaker questions. These are very general, not very general, but these are icebreaker would you rather questions that require you to choose one and then give us just one reason why you chose that that answer. It can be philosophical, it can be practical. You can choose however you would like. Okay,
sounds good.
Good. Yeah. So the first question, there are 5. The first question is, would you rather spend a month writing a grant proposal or a month troubleshooting a stubborn experiment?
I'm going to go with the grant.
Wow.
Yeah, because actually we don't do experiment.
Okay.
So we calculate a lot of stuff by computer. And after I submit the jobs to the computer, and I have to wait sometimes like 1 or 2 months.
Yeah.
Then I have time to write a proposal or something.
Okay.
Yeah.
Okay.
Yeah. We don't spend a lot of time in
troubleshooting experiments. Okay. That makes a lot of sense.
Yeah.
And then number 2, would you rather meet a famous scientist from history like Marie Curie, or be able to see 50 years into the future of chemistry?
Maybe the past time.
Wow.
Yeah. Because I don't see. I can't. I don't see much progress in the future. Actually.
Wow.
Yeah. You can say I'm not that good at science. That's why I'm so.
Of course not.
Yeah.
That's quite interesting. Yeah. That's interesting. I would love to have a follow-up question, but I promised it would only be one. Okay. Okay. And so, would you rather discover a new element or a faster than light particle?
Both of them are too hard for me, I think.
Let's say you could.
Yeah, maybe a new particle. That sounds probably there's a little chance.
I think you may be closer than that, but that's just my opinion. Okay, this one, I have 2 sub-questions. Okay. So, Szeged or Basel?
Which is better or which is worse?
Which one would you Which would you prefer?
Yeah. Now I have to say Basel.
Okay. Yeah. Or Paris or Budapest?
I only went to Budapest first. One time.
One time, okay. Yeah. And you lived in Paris?
Yeah, I lived in... Paris is super good. Yeah. Except at night, which is not safe. But
yes.
But that Budapest has more Asian food, actually, which I like.
Yeah.
So...
Okay,
Yeah.
so okay, that's a good one. And then finally, would you rather simulate CI reactions under extreme temperatures or extreme pressures?
What do you mean CI reaction?
This is the we were talking about this now before we started. The German
Criegee Intermediate.
Criegee, yes.
Okay, I
yes.
see. I thought.
I'm sorry. Yes. So would you rather simulate the Criegee or Criegee? I will find
Criegee
Criegee. Yes.
Intermediate. You mean high temperature or high pressure,
Yes.
right? We did both actually,
Okay.
because I'm not doing experiment.
Yeah.
We use computer.
Yeah.
So for us, the pressure or temperature, it's just a number.
Yeah.
I can write in any temperature, any pressure,
And then
I
you
want. Yeah. So, yeah.
That must be nice. Like it must be more practical than being in the lab.
Yeah. For the experimental guys, it's harder for them to do different temperature or pressure, right?
Yeah.
But computer science is easier.
And it's more modeling than
Yeah.
actual experimentation.
Yeah.
Okay, so that concludes our icebreaker questions. I hope you're relaxed now and you're ready to start.
Yeah. Okay.
Okay, good. So now we're going to get into the part of this conversation about your research, about your work, and I hope normally the people that come here start saying it feels like a thesis defense. So if it starts feeling like that, please stop me.
No, it's okay. I'm not a student anymore. It's okay for me.
Okay, great. So we would like to know what motivated you to pursue research in reaction rate theories and statistical mechanics.
Let me see. At first, as a bachelor, I was a chemist. I did some experiment.
Yeah.
But the problem was that as a bachelor student, I can't get good quality of molecular samples. That's why I changed to theoretical part. Yeah. And the only one professor I can find is doing this work, the reaction rate theory. So that's why I don't have a lot of choice.
Oh, wow. Okay, so then through that you sort of were pushed into that direction.
Yeah.
That's quite that's nice. Okay, and so from your bachelor, you already knew that you were going to be an academic.
Yeah, something like that. I don't remember. At first, I want to be rich. And then I realized that it's too hard, so I changed to academia.
I really like what you said, because I got into academia because I thought there's money and I thought I was going to be rich.
No, it's not.
I have come to realize it has to be about my passion.
Yeah.
And so thank you for that answer. How has I saw in one of your publications that you collaborated with Caltech.
Caltech?
Yes.
What's that?
It was in one of the papers, the institution in California Institute of Technology. I think you wrote something on physical chemistry.
Probably because, as I said, we calculate the reaction rate.
Yes.
And some experimental group, they measure the reaction rate.
Yeah.
So we compare each other.
Yeah.
That's why we collaborated with a lot of experimental groups.
Yes.
Some of them I never seen before, actually. Yeah.
Is it easy to have collaborations with other institutions on your work?
Actually, that depends on the boss. I mean, the professor.
Yeah.
They make this collaboration, and I do the calculations and stuff.
Okay.
Yeah.
Okay, great. Okay, great.
That's why I didn't realize I have
Yeah.
collaborated that Caltech. Yeah.
That is okay. I understand. And also, what breakthroughs do you anticipate in chemical kinetics or reaction dynamics? Do you think there could be some future research in what you do regarding, let's say, reaction dynamics, for example?
You mean the future direction?
Yes.
Yeah. Actually, mainly chemistry is about reaction.
Yeah.
And if you are talking about the reaction, of course, you have to know the reaction rate.
Yeah.
So it's not only one direction. Actually, it's reaction rate is everywhere in chemistry.
Mm-hmm.
So, yeah, I think that's my answer. Okay. Even though it doesn't sound like an answer.
I think it's good enough.
Yeah.
Also because what you do, I think, is very specialized, and it's a niche field that only, I think, a few people know how to do what you do. And I was very impressed because I was like, wow, that's crazy. So now we're going to get into your current research, actually, just to get to know you a bit better as an academic and your background. So I think your most recent paper, as we have spoken about now, is about Criegee or Criegee.
Yeah.
Criegee Intermediate.
Yes.
So I will read here what I found and what it is in simple terms for our audience, and then we'll get into that.
Okay.
Today, I'm diving into the fascinating world of Criegee Intermediates and how these elusive molecules manage to survive under extreme pressure and temperature. Now, you might be wondering, what exactly are Criegee Intermediates? Well, they're highly reactive molecules that play a crucial role in atmospheric chemistry, particularly in the breakdown of pollutants and the formation of secondary organic aerosols. Despite their importance, they're incredibly difficult to study because they exist for only fractions of a second. But here's where it gets interesting. Recent breakthroughs have shown that under certain conditions, these intermediates can be stabilized, giving scientists a unique opportunity to study their properties in detail. Imagine this. We're talking about conditions with pressures up to several gigapascals and temperatures exceeding hundreds of degrees Celsius. It's like putting these molecules in the heart of a diamond anvil cell or subjecting them to laser-driven shock waves. These extreme environments mimic what happens in the deeper layers of the Earth's atmosphere and even in interstellar space. So, how do Criegee Intermediates manage to hold it together? The key lies in the stabilization techniques that involve rapid quenching and trapping methods. By using advanced spectroscopy and computational chemistry, scientists can capture a snapshot of these intermediates in action. What they found is nothing short of remarkable. Criegee Intermediates aren't as fleeting as we once thought. Under the right conditions, they can exist long enough for detailed study, revealing their reaction mechanisms and potential applications in environmental science. This opens up a whole new realm of possibilities. Understanding these intermediates could lead to advancements in reducing atmospheric pollutants and even in the development of new materials. So, next time you think about the complexities of atmospheric chemistry, remember those tiny Criegee intermediates surviving against all odds in some of the harshest conditions imaginable. It's a testament to the resilience and unpredictability of the microscopic world. Thanks for watching. If you enjoyed this deep dive into the world of Criegee Intermediates, make sure to like, comment, and subscribe for more fascinating science content. Until next time, keep exploring.
So Criegee intermediates are highly reactive molecules that form during the breakdown of ozone in the atmosphere, particularly when ozone reacts with alkenes. So these are compounds with double bonds. These intermediates play a key role in atmospheric chemistry, especially in processes like the formation of aerosols and the removal of pollutants. They are very short-lived, but are very important for understanding how pollutants are processed in the atmosphere, influencing air quality and climate by affecting cloud formation and weather patterns. In simple terms, your study generally looked at how changing parts of the Criegee Intermediates affect how fast they break in reactions. So for some CIs, this is Criegee Intermediates, hydrogen atoms move more easily when there's a single bond. But when there's a double or triple bond, another reaction involving oxygen bonding becomes more important. So it adds a layer of complexity. Adding groups like methyl or ethyl speeds up some reactions, while adding unsaturated groups like vinyl slows them down. And one special molecule reacts incredibly fast, forming a ring structure at room temperature.
Yes.
So you then simulate or model how that would happen, and you get your results from there. So my question then, would you like to add something onto that?
No, I think it's pretty good already. Yeah.
Okay.
Yeah.
The first question would be, what is the core significance of this in atmospheric chemistry? So in terms of oxidation processes, especially in controlling the removal of pollutants for air quality.
You mean the most important effect?
Yes.
Yeah. Okay. Criegee Intermediate can be produced by all the green stuff. I mean, trees, grasses, and maybe flowers, and also from industry.
Yeah.
And the main important thing about Criegee Intermediate is that it reacts with SO2 so super fast, and it produces acid rain in the end. So our job is to study if there's less Criegee or more Criegee in the atmosphere, then could we reduce this acid rain or not? Yeah, that's.
And do you think it's possible to reduce the acid rain?
We think that probably we can, but it's super hard. Yeah. For example, you can't cut down all the trees, right?
No.
Yeah, to reduce this Criegee.
Yeah.
Yeah. Of course, trees makes Criegee, but it also makes more good stuff, right?
Yeah.
I don't know what's the good stuff are, but it should be
Oxygen.
Yeah, oxygen, for example.
Yeah.
Yeah, that's why it's too hard. Yeah.
So it's interesting when I'm hearing you say it, because now I'm thinking, if Criegee is sort of found in everything, literally everything, then maybe it's the amount that it is emitted from trees that is not as much as like anthropogenic influences.
Probably yes. It's because it's hard to measure how much Criegee is in the air, because you may notice it from its name, Criegee Intermediate.
Yeah.
Intermediate means it's very unstable, so we don't know how much was there. For example, how much Criegee one tree can make per day or something. It's hard. It's hard to measure.
And we cannot model that computationally.
Yeah, we can, but there are so many uncertainties. Yeah.
Okay.
Yeah.
Okay.
Yeah.
And so these advances in your research, how do they help us to understand these intermediates?
Because we collaborated with experiments. Of course, I shouldn't say this, but you should trust the experimental results more than us.
Yeah.
But for experiment result, they only have the final result. I mean, what is the reactant, what is the product, what is the reaction rate, and so on. They don't know why it's fast, why it's slow, and why it can produce this product, not the other product. Yeah, they don't know that. That's why we can help as a theoretical study. We simulate it on the computer. We can see how the reaction occurs from one step by one
To
step.
another.
Yeah.
And just how much computational power do you need? Is it like a lot of data?
Yeah. The bigger, the better. I mean, if I have more computers, I can publish more papers, of course, but I don't have. Yeah, usually we have to compromise. Because we don't have infinite computer and electricity. Yeah.
And how long does it take to run maybe one simulation?
Yeah, it also depends how. Yeah, if we estimate that this calculation may take, for example, more than 1 month, we give up. Yeah, we change to lower cost method to do that.
Okay.
Yeah, but it also shouldn't be too fast. For example, if you can just calculate within 1 second, or you don't even need a computer to do that, then the result is not that good. Yeah.
Okay, I see.
Yeah.
I see. And how do we apply the Criegee Intermediates in climate science? So how it impacts our knowledge for climate-related phenomena like aerosol formation or cloud formation?
I thought I already answered that, but yeah. So first, Criegee react with SO2, makes the SO3, and the SO3 plus water makes this sulfur acid. Yeah, and the sulfur acid helps aerosol and the acid rain.
Okay.
Yeah,
Okay.
yeah.
Yes, you did answer it.
Yeah.
I'm just following my question.
Yeah.
Okay. The final question would be, what advanced techniques or method do you use to study such transient species, and what challenges do you find in observing?
Yeah, you mean advanced? The main challenge in our field is actually the speed of the computer. Yeah, actually, it's the same answer as before. I'm sorry about that. Okay. Yeah, if I have super fast CPU and millions of CPUs, we can do better. Yeah. So the main challenge in our field is that we have to figure out a way to make things faster. I mean, to reduce the calculation for the computer, even though they are fast, but still sometimes it takes 1 or 2 months. So our job is that makes this calculation faster, like within 1 week. Yeah.
Okay.
Yeah.
And what would you do if you had sort of the power to influence how fast the computers go? Or does that have to do with like funding, getting more money to inject into the computers?
Yeah, both fundings and also people, I think. Yeah, you have to have a lot of people working on this and find a way make things faster. Yeah.
And so have you found, I don't know if I'm going to ask the correct question. You can correct me.
Yeah, okay.
So these Criegee Intermediates that you sort of simulate, are they similar for different parts of the world? Or is it like in terms of the acid rain?
What do you mean similar? It's just a molecular. I mean,
the molecular structure is the same. for all different parts. So let's say you want to simulate for Southern Africa and Brazil. Would that give you the same results?
Yeah, of course, it's the same molecular. But if you want to study in different regions of the world, of course, you should consider the different temperature, and the different humidity, and also pressure, and also the sunlight. If you consider that part, of course, the result should be different.
And you can also simulate that computationally.
Yeah, because it's just a number, like a temperature, pressure, and humidity. It's not, you just change the number.
Okay. And so for, let's say, understanding air quality, would you also do the same experiments? So what I'm thinking in my head is when you do these Criegee Intermediates, they show you sort of how the air reacts, or the particles in the air react to certain environmental pressures for climatic events. So if you have different levels of humidity and environmental, let's say, land use, would that be something that you take into account when you are...
Again, it depends. If you want to study the what's the reaction rate for a certain reaction, for example, Criegee with SO2 or Criegee with water, you don't consider other stuff. So, but if you want to see the competition between SO2 and water and something else, of course you put all of them together to see which one can meet the Criegee first, right?
Right. Okay. I hope I managed to ask the correct question.
It is good questions.
And also here, I see that it says for some of these Criegee Intermediates, the hydrogen atoms move more easily when it's a single bond, and then when it's a double bond or a triple bond, meaning another reaction involving oxygen, that becomes more complex. Would you care or like to expand on that?
Of course, if you have more atoms, because Criegee Intermediates, there are several different types of Criegee Intermediates.
Okay.
If you have more atoms, of course it's more complex. As you said, double bond, triple bond, I don't think that's my work. So, so I don't know.
You work with single bonds.
Okay. Because also sometimes double bond.
Okay.
But triple bond that doesn't exist in nature. It of course we can also calculate it. We use computer. It can. You just write in triple bond. You can do anything.
So what would a double bond atom be in nature?
Carbon, two carbon. Two carbon. Double. It's hard to.
I will put it in the screen somewhere and try and show what you're trying to explain.
You mean after this you can put it? Okay.
Yes, I when I'm editing, I'll just put it
maybe later you can write it somewhere. It's two carbon. There's this double bond between two carbon atoms.
Right, and then it's interesting how you say the triple bond would not exist in nature.
Triple bond exists, but a triple bond Criegee doesn't exist.
I see. Okay. And of the challenges that you mentioned to me earlier, how did you overcome them in sort of, like, let's say, the computational power? Of course, you said you have to reduce your expectations, your running time, or maybe add more people onto the project. Is there any other ways you've explored solutions for your challenges?
Not really. I don't know what else we can do. One way is the most powerful method is that ask the professor to buy more computers. That's the most efficient way.
Okay.
Probably.
Oh, and how about AI?
AI also need time. It's the same. We also use some AI to do stuff, but it's slower. Maybe it's smarter, but actually it's slower.
Right.
Yeah.
And of course, you have to use some machine learning methods like deep learning.
Yeah. We also use that.
Yeah.
Because the main time-consuming part in our field is that, as you can see from a resume, we have to get a statistical result.
Right.
Which means we can't only calculate one time. It's not a statistical result. We have to calculate like 1 million times or even more. 1 million is a lower limit, actually.
Wow.
Yeah. So that's why it's time consuming. So AI doesn't help a lot. AI can make the result better, but can't save time.
Right.
Yeah.
Okay. And is there anything you would like to add in this regard?
No, not really.
Okay. And anything about your research you would like to talk about or explore? I'm actually interested in the cutting down of trees.
You can't do that. That's my answer.
Does it mean that the first time I heard of it, I was like, okay, to save an element of like air quality, I assume, or the ozone, or to balance the chemistry there. I'm not sure what I'm saying, but so we have to reduce the amount of trees.
But as I said, trees also make good stuff like oxygen. So that's why you can. Actually, Criegee Intermediates is not that mysterious. It's like O3. It's just a strong oxidant. I don't know if that's the English right name. Yeah. That's why it can change SO2 to SO3 because it has an extra oxygen. That's all.
Right.
It's not very mysterious.
Okay, because I work with trees and I am working to conserve the trees, and I'm thinking if we have to cut down the trees, maybe is it a specific type of tree that emits more of this these intermediates, or it's trees that are in a specific environment, and also maybe to reduce the anthropogenic effect, because you said it's not only the natural parts that are found.
Maybe we can reduce the emit from industry part,
like industry,
not the tree part.
And how about water? Can we how about in water, or it's just only in like trees and plants? And okay, so with the water, I was thinking that the Criegee Intermediate can also be found in water. That's why I was asking that question.
No, you can't find it in water because the Criegee Intermediate can react with water super fast. So once it meets water, it vanished or disappeared.
Okay, so then you are not able to quantify it in a way.
Yeah.
I see.